Class 11th Chemistry, Unit 7 Equilibrium, and in this video we will discuss about di and polybasic acids and factors affecting acid strength. First come to di and polybasic acids. A substance that yields hydrogen ions in solution and from which hydrogen may be displaced by a metal to form a salt is called protic acid. For example, HCl, H2SO4, etc. When this HCl is dissolved in water, it gives hydrogen ion, H plus ion. Or when this HCl when react with the metal, then we will get the salt. Okay, so these are the protic acids. Basicity of an acid is the number of hydrogen ions which can be produced by one molecule of acid. For example, acetic acid, its formula is CH3COOH. Clear? Is monobasic in nature, as it can lose one proton or hydrogen atom to form acetate ion. Okay, in this acetic acid only this H is replaced by the metal, or we can say this proton is loosed by this one. Okay, these three hydrogen atoms which is a part of this CH3 group are not lost. Okay, so this is monobasic acid. If we consider this H2SO4, this is a dibasic acid because these two hydrogens or two protons can be replaced. Acids that have more than one ionizable proton per molecule of the acid are known as polybasic or polyprotic acids. For example, oxalic acid, COOH, COOH. There is a bond between carbon-carbon. Okay, and if we write its molecular formula, then we can write this is C2H2O4. Clear? Or you can also write this is C2O4 and H2. Okay, sulfuric acid, H2SO4, polybasic acid, or we can say this is the dibasic acid. Phosphoric acid, these three hydrogen atoms can be ionized, so this is tribasic acid. The ionization reaction for a dibasic acid H2X can be written like this. In first step, it loses one hydrogen atom and this will convert into HX minus. And for this we can write this is acid dissociation constant, and this is for first step, that's why we are writing Ka1. Okay, and this is the concentration of products divided by concentration of reactant. Now this HX minus in the second step again loses this proton and this will convert into X2 minus. So we can write this is the acid dissociation constant for second step. Okay, and this is again concentration of product in the numerator divided by concentration of reactant in denominator, where this Ka1 and Ka2 are called first and second ionization constants respectively of the acid H2X. For tribasic acids like H3PO4, we have three ionization constants. Now this table represents the di and polybasic acids along with their dissociation constants. Okay, see this is oxalic acid. This is the first dissociation constant 5.9 into 10 to the power minus 2, and second dissociation constant is 6.4 into 10 to the power minus 5. Now just compare this one with this one. The second ionization constant is very less. Okay, if you compare any acid like for sulfuric acid, the first ionization constant is very large, but this is second one is small. If you consider this is phosphoric acid, this is tribasic acid, this is the first ionization constant, this is second, and this is third one. Again you compare. Okay, So that we can say higher order ionization constants like Ka2, Ka3 are smaller than the lower order ionization constant, that is Ka1 of a polyprotic acid. Now what is the reason? Because it is more difficult to remove a positively charged proton from a negatively charged ion or from a negative ion due to electrostatic forces. Actually, after removing one proton, that remaining species will acquire the positive charge. And from that positive charge, removal of proton is difficult. Okay. So, the higher order ionization constants are smaller. And if we write the overall ionization constant, then this is the product of all these. Ka1 multiplied by Ka2, this is multiplied by Ka3. Factors affecting acid strength. The extent of dissociation of an acid depends on the strength and polarity of HA bond. In general, when strength of HA bond decreases, that is, the energy required to break the bond decreases, HA becomes a stronger acid. Also, when the HA bond becomes more polar, that is, the electronegativity difference between the atoms H and A increases and there is marked charge separation, that is, polarity is increased. Cleavage of bond becomes easier, thereby increasing the acidity. Okay. HA bond strength decreases, then acid strength increases. And when HA bond polarity is increases, again acidic strength increases. Okay. In a group of periodic table, HA bond strength is more important factor in determining acidity than its polar nature. Now we are discussing the group, elements in group. Now if we discuss the hydrides of we can say that is 17th group elements. Okay, hydrides of 17th group elements. If we go from top to bottom, that is HF to HI. HA bond strength, that is HX, X is the halogen in general. HX bond strength is decreases from top to bottom, so acid strength increases. Okay, that's why this HI is the strongest acid among these and HF is the weakest acid. Now, if we compare in the period, in the same period of the periodic table, HA bond polarity becomes the deciding factor for determining the acid strength. As the electronegativity of A increases, the strength of the acid also increases. For example, if we consider these are the hydrides of the second period element. If we go from left to right, the difference in the electronegativity of hydrogen and element of second group is increases. So acid strength increases. Clear? Thank you.